This is part 3 of the Module 11 lecture. In this section, we're going to look at the details of the regression model to see how we can interpret the estimates that we calculated using the minimization of the sum of squares. All right. Again, the population regression model is just y equals the parameter for the intercept plus the parameter for the slope times the predictor or the independent variable plus the random error. Now, the mean of the y values for any given x value is given by this equation of the straight line a plus bx. So in this graph, I'm showing you that if you wanted to predict that in an individual value, in addition to the two parameters, you also need to know the random error associated with that specific observation. However, if you are interested in predicting the average value of y at any given value of x, is just a plus bx. Right, with that in mind, then when we look at the sample regression line, or what's sometimes called the least squares regression line, then in this case, if you notice, this equation resembles this equation, the question for the mean. So then it makes sense that this y hat of this is an estimate of, or a point estimate of the mean of y for a given value of x. So when you use the values of a and b that you calculated, and then you want to find a value of y for a given value of x, what y hat is going to be is a point estimate of the average of y for the value of x that you put into the equation. So this y hat is an estimate of the mean of y for the value of x. So this is very important. So the values you calculate from this equation are estimates of the mean of y for some value of x. So this is very important as was a very important consideration as we interpret the coefficients, or rather the estimates of a and b and the predictions that we make with this model. All right, let's see how we interpret the coefficients. So the intercept is just the mean of y when x is equal to 0. And one important thing to keep in mind is that if x equals to 0 is not in the range of the observed values of x, then the intercept may not have a meaningful interpretation. An example that came to mind as I was thinking about this is that, for example, when you invest money to advertise a product, and then you see how much sales you're getting per dollar invested in advertisement. And let's say that the line that you fit to the data has a negative intercept, and you never collected data for the amount of sales when the amount of advertisement is 0. So that means that if you were to, you could say that for 0 advertisement, then you have negative sales, which doesn't make any sense. So you need to be careful when you are interpreting the intercept, is to look at the data and see if you have values that include the x equal to 0. If the data does not include that value, then interpreting the intercept may not make any sense. So be careful with that. All right, so in the interpretation of the slope, which is really the more important aspect of the regression and simple regression analysis, is b is the average value or the average change in y per each unit change in x. Let's see how we do this with the example of that we've been working with, of the GPA versus the hours worked per week. So over here I have the model that or rather the sample regression model. So here's the intercept and here's the slope. So we say that the y-intercept corresponds to the mean of the average GPA of all the students that work 0 hours per week. That means they have a work outside from their work they do as a student. So using this equation, then you set x to 0, and of course this term is 0, and so y at x0 is just 3.34. That means that on average, students that do not have a job outside school, in other words, we say they work 0 hours per week, have a GPA or an average GPA of 3.34. And this is a valid prediction because we have data for students that work 0 hours. So this interpretation is meaningful. All right, so that's the interpretation of the intercept. The interpretation of the slope is the estimate of the average change in GPA per each hour worked. So an increment of 1 hour worked per week will decrease the GPA by 0.0297 points. And why decrease? Well, because the sign of the slope is negative. So as you increase the hours, then the GPA decreases. And again, this estimate is only valid in the range from 0 to 40 hours because that's where we have data. We don't have any data beyond 40 hours per week. All right, so this is how you interpret the coefficients. Now, how would you interpret predictions from the model? Now we're addressing the issue that we started with, where this student is working 8 hours per week and he wants to see what will happen to his GPA if he works 16 hours per week. All right, so we're gonna calculate the average GPA for students that work 8 hours, students that work 16 hours, and students that work 30 hours. So to do this, we use the sample regression equation, and we just plug in those numbers. So we want to see what is the expected average GPA of students that work 8 hours. So x now is equal to 8. We put that into the equation, multiply that by this, and then that product is subtracted from this because of the negative sign. And so we say that, and that result is 3.096, which is what I'm showing here in the graph. So that on average, we can say the students that work 8 hours per week have a GPA of 3.096. All right, so now if a student works 16 hours per week, we plug in the 16 hours into the regression equation, and now we find that is 2.859. So students working 16 hours per week have on average a GPA of 2.859. So given this result and the previous result, then the student can make a decision if he's willing to take a reduction in GPA on average of this much. Right? Now, in the last case, we wanted to see the average GPA of students that work 30 hours per week. And you can see by putting 30 into the equation, we get that GPA is 2.443. So we can say then that the average GPA of students working 30 hours per week is 2.443. And again, if you're curious about 40 hours, well, you can plug in 40 here and calculate the GPA value. But now this is how we can make predictions and then how we interpret these predictions. And the key word is we predicted an average GPA in this case. All right, now be careful when you use regression. Regression is known to be one of the most used tools, but one of the most abused tools in practice. So again, a regression model, when you're fitting a simple regression model, you're making the assumption that the linear relationship between y and x, or rather the relationship between y and x is linear. Or very specifically, for simple linear regression, you're making the assumption that y depends on x linearly. In other words, that dependency follows a straight line. So a straight line model can be fitted to any data. Whether the data is straight or not, the numbers will produce some estimates. So, for example, in here, if we have this true relationship between x and y, and we just fit a regression line, well, we will get an estimate of a and b, and we will think that we have a model. But really, that true relationship is not linear. So you have to be careful. And later on, we will learn to do what is called residual diagnostics to see if we have this situation. Right? But one of the cautions is be careful, because a true linear relationship may not exist. But you may think that it exists just because you fitted the equation. And that is not necessarily true. Another important caution is when perhaps you fit a straight line. I'm using the same function here. Let's say that you collect the data between 35 and 45. You fit the data and you do all your residual diagnostics, and so you have a really nice model. And sure enough, in this range, this part of the curve can be well represented by a straight line. But the problem is, if you start trying to make predictions outside that range, those predictions will be incorrect, because then the behavior is no longer that of a straight line. So you have to be very careful. So what we call extrapolations, meaning making predictions outside the range of the data that you collected, is not a good idea, because we really don't know the true behavior of the actual relationship between x and y outside that range of data. So you have to be careful for making predictions outside that range. All right, so going back to the model that we were fitting to the data. So in the GPA versus hours worked per week, the hours worked per week span from 0 to 40 hours per week. So if the relationship between GPA and hours worked per week follow a straight line, then the regression model that we fitted to that data will produce realistic predictions of the average GPA only in the range from 0 to 40 hours. So two big assumptions. Number one, this is a true relationship of GPA on the number of hours worked per week, and predictions made with this model can only be for 0 to 40 hours per week, because that's the only range of values that we obtain data for. All right, so you need to keep this in mind when you use your regression model to make predictions. All right, in the next recording, we will talk about the regression errors and the coefficient of determination.